We investigate differences in muscle activation when an expert versus a novice draws a circle while there are external constraints. Here we have the novice drawing the circle without any external constraints, and as we can see, there is a high EMG activity across all muscles, even between antagonist muscles, because they tend to be bracing the arm to stabilize hand movements because fine control is lacking. And here we have the expert drawing the same circle without any external constraints, and as we can see, she only activates relevant muscles during the different phases of the circle drawing, showing much more muscle control. Now we have the novice drawing the circle while there is a constant force attached to his pencil, and we see that there is a sharp increase in EMG across all muscles, and there is a more noisy pattern as well. The novice cannot finely adjust force output to compensate for the external load, and instead they increase overall muscle tone to fight the unknown forces. Now the expert draws the circle in the same constant force condition, and we see that while there is a mild to moderate increase in EMG signals, but the pattern remains smooth, meaning that the expert is predictively compensating for the constant force, and they are slightly increasing activation of muscles that oppose the external load direction. Now we have the novice drawing the circle while there are random external perturbations, and we see that there is a delayed EMG response at the perturbation onset, which is shown by the black line, which means that the CNS responds after the disturbance has happened. And the broad, messy, and large EMG bursts indicate poor force tuning, showing that the novice uses sudden and imprecise corrections to account for the external load. Now we have the expert drawing the circle while there are random external perturbations, and we see that there are small sharp EMG spikes around the perturbation event, which means that there is feed-forward control, meaning that the expert anticipates likely disturbances and pre-activates stabilizing muscles. There is also a quick return to baseline activation, which means that the expert integrates sensory feedback into motor planning almost instantly, or at least faster than the novice. Overall, this shows that experts have better internal models of limb dynamics. Their CNS predicts external disturbances and integrates feed-forward control with fast feedback corrections, whereas novices rely heavily on sensory feedback, which is slower, leading to overcorrection and instability. And mechanical impedance is used selectively by experts and globally by novices because they co-contract everything just to be safe.